Hi everyone. Today I want to explain the concept of prokaryotic replication. Remember that prokaryotes are simple organisms like bacteria and archaea, and they are some of the simplest life forms on Earth. Replication is the process of making exact copies of DNA so that it can be transcribed into RNA and translated into proteins at a later stage. So today we'll just be explaining replication and how it works in detail within prokaryotic organisms. Prokaryotic DNA is contained within a single loop that is often somewhat disorganized. This simple blue loop is a good illustration of what it would look like if it was laid out flat against the board. If we were to zoom in on this tiny black box, we would see something like this Lego piece at the molecular level. Imagine the blue strips are the actual building blocks of DNA. Well, DNA is composed of sugars that are connected through 3' and 5' regions back to back, and they are specifically connected through phosphodiester bonds. Imagine the 5' region to be these blue connection points, and the 3' regions to be these red connection points. This gray piece at the left side is the origin of replication, and this is where replication will begin. Replication involves the work of many proteins and enzymes to help get the job done. In our example, gyrase will be represented by this red circle, primase by the cream-colored brick, ligase by this brown brick, DNA polymerase 3 by this white triangle, DNA polymerase 1 by this gray round piece, helicase by this green triangle, and single-stranded binding proteins by this orange circle. Gyrase has the job of relieving torsional stress from supercoil. Supercoiling occurs when that original blue circle of DNA that I'm showing now becomes twisted and kind of disorganized, as I've shown on the right. Gyrase will connect near the origin of replication and relieve stress from supercoiling. Next, helicase will bind and begin to separate the DNA into single strands like this, in kind of an unzipping fashion, so that the DNA can be copied. And we'll do this traveling from the left to the right direction. Next, single-stranded binding proteins will bind to individual strands of DNA so that it is stabilized for replication. Now that single-stranded binding proteins have attached, we will begin replicating the strands of DNA individually. We'll start with the top strand and zoom in. We'll be focusing here on this top strand, and as you can see on the left, we have the 3' end because it's red, and on the right we have the 5' end because it's blue. So DNA polymerase will begin breeding in the 3' end to 5' direction, and we'll be adding DNA in the 5' to 3' direction. So that would look something like this. Now this strand is called the leading strand, because DNA polymerase is able to continuously synthesize DNA in the 5' to 3' direction, falling behind helicase as DNA is unwound. The bottom strand is also called the lagging strand. It must first be prepared for synthesis because the direction of helicase unwinding is opposite to the direction that DNA polymerase 3 reads and synthesizes. First, primase creates an RNA primer which DNA polymerase 3 is able to begin synthesizing off of. The primer will later be removed by DNA polymerase 1, and then these short pieces of newly synthesized DNA are called Okazaki fragments and will become connected by ligase to form a continuous DNA sequence. This new DNA segment that was connected by ligase is of course in the 5' to 3' direction. Once helicase finishes unwinding the entire segment of original DNA, we're left with 2 duplicate sequences of DNA. One last thing I'd like to discuss is what would occur if DNA polymerase 1 was not functioning correctly. Remember that DNA polymerase 1 is responsible for removing RNA primers from Okazaki fragments. So if it was malfunctioning, the Okazaki fragments would never be able to be connected by ligase, and the lagging strand would never complete replication. This would result in only half of the products of replication being created, as only the leading strand would actually finish. That's the end of my demonstration of prokaryotic replication. I hope you will remember that replication is an important cellular process that results in the creation of 2 identical copies of an original DNA sequence so that transcription and translation may occur later on. I hope you enjoyed.